Okay, so thank you all very much for coming today. So I'm going to start out with sort of the high-level overview of how you run simulations with OpenMM. And then after this, Walker will be going through all of this in much, much more detail and giving you lots of exercises to actually do it for yourself. So I always find it a bit difficult to explain exactly what OpenMM is. So instead of telling you, I'm just going to ask you to tell me. We're going to start out with a quiz. OpenMM is A, is it an application for running molecular simulations? B, is it a library of simulation routines for use by applications? C, is it a domain-specific language for molecular simulation? Or D, all of the above? You get 3 guesses, and anyone who gets this wrong, well, okay, who's going to tell me? Which one is it? Smart, yes. It is all of the above, because I would never ask this question if the answer were not D. Yeah, so OpenMM actually is all of these things, and it can be used in many different ways depending on what your purpose is. So let's go into that in a little more detail. So what is OpenMM? It really consists of 2 major pieces. First, there is sort of a low-level computational library. It is written in C++, and what it provides is an API that you can use in your own applications. You can tap into this library, and that library provides lots and lots of computational features that you would want in any application that needs to do molecular simulation. It knows how to do things like evaluate force fields, compute forces and energies, perform numerical integration, that sort of thing. Now, sitting on top of that, we have another layer that we call the application layer, which is written in Python. And this provides sort of the higher-level routines that make this into not just a set of low-level computations, but actually a full application. This layer is where it knows how to do things like load a PDB file, save a PDB file, load a definition of a force field, and build a molecular model based on that force field. So depending on what your interests are, you might be working at either or both of these layers. And we'll be talking about both of them as the day goes on. It is written to be very hardware agnostic. The API in particular is really designed to say nothing about what kind of hardware you're running on, so that we can then have different implementations of that API that are optimized for different types of hardware. In particular, we have 3 different implementations currently. 2 of them are for GPUs. One uses CUDA, which is NVIDIA's proprietary system they've developed for programming their GPUs. The other is OpenCL, uses OpenCL, which is a cross-platform toolkit or technology for programming GPUs that's supported by many different vendors. And then we also have a reference platform that is written in C++ and just runs on your CPU. The goal of this is to be able to directly address several very distinct types of users. So first we have sort of biologists and chemists, the people who want to run simulations to, study biology, study chemistry, learn something about a biological or chemical system. And these people will use the application layer to run simulations. Second, we have application developers, people who are creating a molecular simulation-oriented application. And those people will make use of the low-level OpenMM library to implement features within their application, such as evaluating forces, evaluating energies, performing integration, and so on. And then there's also a third group that OpenMM is really sort of uniquely suited towards the needs of these people, which is people who are developing new algorithms, developing new methodologies for molecular simulations. And these people can use both the Python and C++ layers to develop new algorithms, and they also can use some features that we'll talk about later that are quite unique to OpenMM, called custom forces and custom integrators, that allow you to very, very easily develop completely new algorithms. So let's talk about how you run simulations in OpenMM. So I keep calling this thing an application layer rather than an application, because it's not quite the same. Really, what we call the application layer is just a set of Python libraries. And it's not like a complete self-contained application in itself. Really what you do is you write a Python script that is really the application that makes use of these libraries in order to run a simulation. So let's take a quick show of hands. Raise your hand if you're an experienced Python programmer. Hey, we've actually got several. Great. If you're an experienced programmer in any language. We've got most people here. And the rest of you are thinking, what the heck am I doing here? I obviously don't belong in this room right now, right? No. Don't worry. No programming experience is required to do this. Now, here's how I think about this. In pretty much any MD application, you're going to have to write some sort of a control script that tells it what you want to do, what algorithms to use, what simulation to run, etc. And it just happens that in OpenMM, that control script is written in Python. But that doesn't mean it's any harder to write than the ones in any other MD application. In fact, I think it's a lot easier to write. I mean, maybe that's just my bias because I'm a programmer. But, when I look at these control scripts like in Amber that has line after line after line of, 2 or 3 letter abbreviation equals whatever, I find those completely opaque and unreadable. So it's actually really easy to write these control scripts, and no programming experience is required to do it. And in most cases, what you'll do is you'll just take a pre-written script that we provide for you, and you'll just modify that in particular very well-documented ways to make it do exactly what you want. And so I think the easiest way to dive into that is let's just look at a script. So here we have a complete Python script that runs an MD simulation. About a dozen lines here, and in this this dozen lines, we do absolutely everything from loading in a PDB file, loading a force field, setting up your system, integrating it, or doing an energy minimization, running a simulation, outputting results to a PDB file, all that in basically a dozen lines. And so I'm going to walk through the script with you now and just show you sort of line by line exactly what it's doing, and you'll see how easy it is to modify the script to do exactly what you want for your simulation. All right. Starts with 3 lines at the top that I'm going to tell you don't even worry about them. All those lines are doing is telling the Python interpreter, here's some libraries we're going to use. Include them at the top of your script. Don't worry about what they mean. OK, next line, load in a PDB file. In this case, we're saying our PDB file is called input.pdb. Obviously, you can change that to specify any file you want. Now, technically, what we're actually doing here is we are constructing a PDB file object. So PDB file is the name of this class, and we invoke its constructor and pass in the file name, and this creates a new PDB file object that we assign to a variable called PDB. Good to know that's what it's doing, but you really don't need to worry about that if you're not a programmer. Just, this line loads the PDB file, fill in the name of your file there. Now we've loaded a PDB file. We want to simulate it using some force field. So here we create a force field object, and we assign it to a variable called force field. And just as in the previous one, we passed in, the name of this file called input.pdb that we wanted it to load. Well, in this case, we tell it what file or files to load that have the force field definition in it. In OpenMM, force fields are defined by XML files, and it has a whole bunch of them that are just built in that define a bunch of standard force fields. But you can actually write your own XML files if you're into force field development. And if that's something you're interested in, I think there will actually be a talk on that tomorrow. Is that? Or is that tomorrow or later today?
I think it's this afternoon.
OK, so you'll actually hear a bit about force field development. So in this case, we are telling it we want to use the Amber 99 SB force field, really common force field, and that we want to use the TIP3P water model. So we've done that. We've loaded our PDB file. We've set up the force field we want to use. Now we need to combine them and say, OK, model this, this molecule that we loaded from our PDB file using this force field. And we do this with forcefield.createSystem. And we pass into it a number of options that you can use to customize exactly how it's going to model your system. So, it has here pdb.topology. Don't worry about that. It's just saying use the information, the topological information that was loaded from the PDB file. And then it's specifying some options like We want to use the particle mesh AWOL method to model long-range interactions. We want to use a 1 nanometer cutoff on your non-bonded interactions. We want to constrain the lengths of all bonds that use a hydrogen. And there are a bunch of different options that you can pass in here. They're all described in a lot of detail in the manual. And so this is just sort of where you say, OK, time to model our system. This is how we want to model it. All right. We've described how we want to model the system sort of in terms of the force and energy description. Now we're going to want to simulate it using some integration method. And we need to describe how we're going to do that. So in this case, we're going to use Langevin integration. It's a standard method supported by pretty much all MD applications. It's a stochastic integration method that simulates your system coupled to a heat bath. And so we simply create a Langevin integrator object and assign it to the variable integrator. And we pass in some options here. In this case, we're saying the temperature to simulate at is 300 Kelvin. We're going to have a friction coefficient of 1 inverse picosecond and a time step of 2 femtoseconds, or 0.002 picoseconds. OK, so you've loaded your PDB file, you've selected your force field, you've described how you want to model your system, you described what integration method you need to use. Time to say, OK, let's perform a simulation. And you do this, guess what, by creating a simulation object and assigning it to a variable called simulation. And we just give it the information from all the previous steps. So the topology that we got from our PDB file, the system that we created from our force field, the integrator. And this just says, we're starting a simulation. And it's actually possible to have many of these simulations if you want to sort of be doing multiple simulations in parallel. And for example, if you're going to be passing information back and forth between them, but don't worry about that right now. One thing we do need to tell it is, yeah. So we'll talk about that a bit later, but the system is actually not really, so okay. Topology basically describes the chemical structure of your molecule. It says we have this set of atoms that are characterized, these elements. They are connected by bonds. It's sort of a chemical level description. System is more a mathematical description. It says this is the, basically, this is the potential function describing our system. It has, instead of where a topology says, we have a chemical bond between these two atoms, the system will say, we have a harmonic force term connecting these two particles with this spring constant, et cetera. So they really are different information. We do need to tell it what we want to use as the starting positions for a simulation. So we just say set positions, pass in the positions that were loaded from our PDB file. Now, frequently before you start a simulation, you want to do some sort of an energy minimization, especially if it's like a PDB file you downloaded from the protein data bank. Who knows what these coordinates are? They may be like from NMR or crystallography. They probably aren't at any sort of a minimum for the particular energy function you're using. And so, if you just started from that, you'd get it, it would just blow up instantly because you'd have all these huge forces. And so usually it's good to start by doing a local energy minimization. And in OpenMM, that's one line. Simulation.minimize energy, you're done. Now it's minimize the energy. One more thing we want to do, you're probably going to want some sort of output from your simulation. And this line here is telling it that we want to periodically write states from our trajectory to a PDB file. We say we're going to call that file output.pdb. You can, of course, change that to whatever name you want. We tell it to save a frame to this file once every 1,000 time steps. And there are other options you can do here. Notice that what we're really doing is creating a PDB reporter object and adding it to the simulations list of reporters. There are other kinds of reporters that we also have that will output other types of information or output trajectories in other formats. And this is all described in the documentation. And finally, simulation.step 10,000. This says take 10,000 time steps. And that will do it. It will run a simulation for 10,000 time steps. Every 1,000th time step, this reporter will output a state to your output.pdb file. And that's kind of it. And does that all make sense pretty much? Excellent.
I have a very main question.
Yeah.
What is the difference between this Python script and
So, right. So conceptually, they're doing the same thing. What is different about this is that this is a real programming language. Amber has a very, very specific set of hard-coded features. It has, all this huge list of like 2- and 3-letter abbreviations that you say, ABC equals 5. And as long as they're doing, and this is true of pretty much nearly all other MD packages, they have sort of a very fixed set of features. And as long as you're doing one of the things that they have built in as a feature, you're fine. And as soon as you want to go outside their list of built-in features, it either is very difficult or impossible. In this architecture, it's very, very easy to customize it in a huge range of ways. And you'll be seeing a lot of examples of this later on of just how powerful this architecture is. Yeah.
So would you say then create that Amber equals 1 and just PDP Amber? Or?
Funny you should ask about that. Yeah, so in the last slide, or that last example, we were starting from a PDB file and a force field and saying model it with a PDB file. We also support using the Amber Tools package to set up your system, and then you can use those input files that were generated by Amber Tools as the starting point for a simulation in OpenMM. And here's a complete example that works that way. It's almost identical to the previous one, and in fact, let me just highlight, the things in yellow are the only things that are different. So really, all that is different, the previous example started by loading a PDB file and a set of force field files. Well, in this case, we load an Amber parmtop file and an Amber input chord file. And then virtually everything else is identical between them. And this is very useful because Amber Tools is a really powerful package that can do all sorts of things for sort of, initial setup of a simulation. For things like, building missing parts of your system, adding water box, filling in parameters for small molecules that you may want in your simulation, et cetera, et cetera. OpenMM does have a limited set of things like that. It knows how to do some basic things like add a water box. It can add missing hydrogens. But it's pretty limited still in what it can do with that. Like, it can add hydrogens, but it can't add any other missing pieces. So, like if you've got a missing loop or, maybe one of your side chains is missing its tail or something like that. If you have a small molecule that we don't have built-in parameters for, OpenMM doesn't have any built-in modeling features for using that. And so if you want to do that, what we recommend is you use the Amber Tools package, and it will create these files, and then you can just load them directly into OpenMM. So that is sort of the end of this introduction, and next Walker will be walking you through much more detailed examples of all of this. Any more questions before we move on to that? Okay.